There is a desert at the edge of the world where the night arrives like a held breath. No wind, no sound, just the vast, open dark, and beneath your feet, a cold that seeps upward through layers of sand and stone and time. The Gobi stretches across nearly 2 million square kilometers of Central Asia, larger than most countries, older than most names. At night, under a sky crowded with stars that have no competition from city light, it becomes something stranger than a place. It becomes a feeling. Most deserts have a quality of forgetting. The Sahara forgets in heat, the Antarctic forgets in ice. But the Gobi forgets in silence, a particular, deliberate silence that feels less like absence and more like concealment. As if the land knows something and has decided, long ago, not to speak. Walk far enough into certain regions of the Gobi, and the surface changes. The sand gives way to something harder, something that catches the starlight in ways sand should not. You crouch down, and your fingers find it before your eyes do, smooth, cold, curved slightly at the edges, translucent in the way that glass is translucent. It is glass. Buried in one of the most remote stretches of land on Earth, lying beneath the surface in fields that stretch for kilometers, is glass. Not bottles, not fragments of ancient trade. Glass that was born here, formed in this place, fused from the very sand beneath your feet by a heat so extreme it defies any ordinary explanation. This is not a story that begins with speculation. It begins with a substance that should not exist. Volcanoes produce glass. Meteor impacts produce glass. These are the two mechanisms that geology accepts without argument, the two paths by which sand transforms into something rigid and luminous. But the Gobi has no volcanic history in the regions where the glass appears. There are no lava flows beneath the surface, no magma chambers in the geological record, no ash layers that would tell the story of an eruption old enough to have been forgotten. And the meteor impact explanation, the instinctive, obvious reach for a cosmic answer, runs into its own quiet complications when researchers examine the glass more closely. The craters are missing. The dispersal patterns are wrong. The chemical signatures point somewhere that the standard explanations cannot quite reach. What you are about to hear is not a theory invented to entertain. It is a genuine, unresolved scientific anomaly, one that has attracted the attention of geologists, cosmochemists, archaeologists, and climatologists for decades, and that has stubbornly refused to yield a clean, satisfying answer. The researchers who have spent careers studying this glass are not fringe voices. They publish in peer-reviewed journals. They present at international conferences. And they will tell you, in the careful language of science, that the Gobi Glass does not fit. Not comfortably. Not completely. Not yet. There is a particular quality to a mystery that is real. It doesn't announce itself loudly. It doesn't demand your attention with noise and spectacle. It simply sits there, patient and quiet, glinting in the dark, waiting for someone to crouch down and ask the right question. The Gobi Glass has been waiting for a very long time. What created it? What event, occurring in a place that now knows only cold and silence, generated temperatures capable of fusing sand into glass across hundreds of kilometers? What was here before it happened? And what or who was standing on this ground when the sky, in whatever form the sky's violence took that day, came down? The desert isn't talking, but the glass is. And this is what it says. Long before any geologist ever crouched in the Gobi with a sample bag and a field notebook, the people who crossed this land already knew that something was wrong with it. The Silk Road, that ancient web of trade routes connecting China to the Mediterranean, threaded through the edges of the Gobi for centuries. Merchants, pilgrims, soldiers, and wanderers moved through these corridors carrying silk and spice and ideas in both directions, pausing at oases, following paths that had been walked into the earth by generations before them. And in the accounts of those travelers in journals and itineraries and cautionary notes passed from one caravan to the next, certain regions of the Gobi appear with a persistent, uneasy reputation. Traders described ground that looked burned, ground that glinted in ways that made animals nervous, ground that the local guides called, in several different languages with several different words, some version of the same thing, the place where the sky fell. They didn't stop there. They didn't investigate. They moved through quickly, keeping their eyes forward, and they told the people who came after them to do the same. This was not superstition for its own sake. Nomadic cultures that depend on reading the land for survival develop an acute sensitivity to anything the land communicates. When the ground looks like fire touched it, and no fire in living memory has touched it, the message is clear enough. Something happened here that we don't understand, and it is wiser to respect that than to probe it. The first modern geological accounts of anomalous glassy material in the Gobi region appeared in the early 20th century, filed by surveyors working for Russian and Chinese geological agencies conducting broad regional assessments. These early reports were careful, technical, and in the way of scientific documents that describe something without a category quietly ignored. The surveyors noted the glass, described its distribution, measured its properties as best they could with the instruments available, and then moved on to the next finding. The reports were catalogued. They sat on shelves. This is not unusual in the history of science. Anomalies that don't fit the current framework tend to be shelved rather than confronted, not out of dishonesty, but out of the practical reality that science advances most efficiently by consolidating what it understands before it challenges what it doesn't. A strange glass field in a remote desert, in an era before satellite imaging and isotopic mass spectrometry, was simply not a priority. There were more pressing questions. The glass could wait. Among those early surveyors was a Russian geologist whose field notes, only partially translated into English and still largely unpublished outside of specialist archives, described the glass formations with unusual care. He noted that the deposits were not random. They appeared in discrete clusters, separated by stretches of ordinary sand, arranged in a pattern that reminded him. And he wrote this, with the hesitation of a scientist, to aware he was on uncertain ground of the distribution pattern left by an event, rather than a process. Processes are gradual. Events are sudden. The glass, he wrote, looked like evidence of something that happened all at once. Decades passed. The glass waited. By the mid-20th century, as geological survey technology improved and the Gobi region became more accessible to international researchers, the scale of the glass deposits began to become apparent, and scale, in this case, was the detail that could no longer be shelved. A single patch of anomalous glass in a desert might be a curiosity. Glass fields stretching across hundreds of kilometers, appearing in multiple discrete regions across a vast geographic corridor, is something that demands a name and an explanation. The bigger the anomaly, the harder it becomes to explain away. Researchers who began their investigations expecting to close a minor geological mystery found instead that every answer they reached for opened a larger question. The glass was not a footnote. It was a headline written in a language that science was only beginning to develop the tools to read. The traders on the Silk Road had been right about one thing. Something had happened here. Something worth remembering. To understand why the Gobi glass is strange, you first need to understand what glass is and what it takes to make it. Glass, in its natural form, is what happens when certain minerals are exposed to extreme heat and then cool rapidly. Sand is mostly silicon dioxide, one of the most common compounds on Earth's surface. Under ordinary temperatures, it is sand-loose, granular, soft enough to slip through your fingers. But push its temperature past approximately 1,700 degrees Celsius, and something changes. The crystalline structure that makes it sand breaks down. The material melts. And if that melt cools quickly enough, it doesn't have time to reform into crystals. It freezes instead into a disordered, rigid, transparent solid. It becomes glass. Lightning does this on a small scale. When a bolt strikes dry sand, the intense heat along the strike channel fuses the grains into a thin, branching tube of glass called a fulgurite, a glass fossil of the lightning itself. You can hold one in your hand. It is delicate, fragile, and roughly the width of a finger. The Gobi glass is nothing like a fulgurite. It comes in sheets and slabs and irregular masses, covering areas that no lightning bolt could approach. Whatever made the Gobi glass was not working on the scale of a lightning strike. It was working on the scale of something that dwarfs almost anything in the natural world. There are naturally occurring glasses that researchers use as reference points. Tektites form during meteor impacts, when the energy of a cosmic collision melts both the impactor and the target rock, spraying glass droplets across wide areas. Trinitite is another reference, a greenish glass found at the Trinity nuclear test site in New Mexico, where the first atomic bomb detonated in 1945, fusing the desert floor in the same way a cosmic impact would. Both trinitite and tektites have well understood chemical signatures. They carry the fingerprints of the events that made them specific ratios of oxygen isotopes, trace elements absorbed from the impactor, pressure signatures embedded in the crystal structure of minerals caught in the blast. The Gobi Glass has been compared to both. It shares some characteristics with each. But when researchers analyze the isotopic ratios and trace element profiles in detail when they read the glass as a document, the message is not clean. Some markers point toward a cosmic origin. Others do not match any known meteoritic glass in the database. The pressure signatures are inconsistent with a single point impact, and certain elemental concentrations appear in proportions that don't correspond to any catalogued meteor, any known volcanic system, or any geological process that operates at the Earth's surface. The glass exists. That much is certain. What created it is the question that remains, patient and unanswered, waiting in the chemical record for someone to find the right frame. Something made it. Something extraordinary. And the evidence keeps pointing somewhere that no one has yet been willing to follow all the way to the end. To understand what may have happened in the Gobi, you need to stand in a very different world, not the world of nations and names, but the world as it existed roughly 12,000 years before the present, when the Earth was in the middle of one of the most extraordinary periods in its recent history. The last great ice age was ending. For tens of thousands of years, ice sheets several kilometers thick had covered much of the northern hemisphere, pressing down across North America, Europe, and northern Asia, with a weight that actually bent the crust of the Earth beneath them. Then, gradually, the ice began to retreat. Temperatures climbed. Glaciers pulled back from coastlines, uncovering land that had not seen sky in millennia. Sea levels rose as that frozen water returned to the oceans. Ecosystems rebuilt themselves, species moved into newly available territory, and early human populations spread across landscapes that were, for the first time in living memory, becoming livable. The world was warming. The long cold was ending. And then something stopped it. Approximately 12,900 years ago, within what appears to have been a span of decades, perhaps less, the temperature in the northern hemisphere dropped dramatically. Not gradually, not in the way that climate change usually moves, across centuries and millennia of slow adjustment. In what geological terms describe as nearly instantaneous, average temperatures in parts of the northern hemisphere fell by as much as 10 degrees Celsius. The warming stopped. The ice sheets stabilized. The grasslands that had been reclaiming frozen territory contracted. The megafauna, the mammoths, the mastodons, the giant ground sloths, the short-faced bears, began disappearing from the fossil record at a rate far exceeding anything that climate alone could explain. And the early human populations that had spread so confidently across the warming landscape found themselves suddenly, terrifyingly, cold again. This period is known as the Younger Dryas, named for a small alpine flower whose pollen appears in sediment cores exactly when temperatures crash a botanical timestamp on a planetary disaster. It lasted roughly 1,200 years, from approximately 12,900 to 11,700 years ago. For the people living through it, those 1,200 years were not a geological curiosity. They were the entirety of their world's memory. They were the great catastrophe, the time before which everything was different, and after which nothing was ever quite the same. For decades, the Younger Dryas was explained as a climate event, a disruption of ocean circulation patterns. Specifically, the weakening of a current called the Atlantic Meridional Overturning Circulation, caused by a flood of fresh water from melting ice sheets. This explanation is plausible. Ocean circulation does drive climate. Fresh water disrupts that circulation. The model works, to a point. But a growing number of researchers have become convinced that the Younger Dryas was not, at its origin, a climate event. It was something that triggered a climate event. Something that happened so quickly and so violently that the climate system had no choice but to respond in the only language it knows: temperature. The leading version of this alternative explanation is called the Younger Dryas impact hypothesis. It proposes that a fragmented comet, or a swarm of cosmic debris, struck or exploded over the northern hemisphere. approximately 12,900 years ago, triggering massive wildfires across multiple continents, sending enormous quantities of particulates into the atmosphere, disrupting the ice sheets, flooding the fresh water into the oceans, and setting off the cascade of effects that we label the Younger Dryas. The Gobi Desert sits within the broad geographic corridor where such an events reach the heat pulses, the shock waves. The secondary fire effects could have arrived with force sufficient to fuse the ground itself. This is not a comfortable hypothesis. It requires accepting that the sky can fall, and that when it does, it changes everything. But the evidence for it has been accumulating for nearly 2 decades, piece by piece, in the way that inconvenient truths tend to accumulate quietly, persistently, until the weight of them can no longer be set aside. When most people think of the Gobi, they picture the landscape that exists today, the grey-brown expanse of gravel and hardpan, the scattered dunes, the absolute absence of anything that could be called welcoming. It is a desert in the fullest sense of the word, a place defined by what it lacks: water, shade, forgiveness. But this landscape is not permanent. It is not even particularly old. The geological and paleoclimatological record tells a different story about the Gobi, one that has been assembled slowly. From lake sediment cores drilled by researchers in Mongolia and China, from pollen analyses conducted on ancient lakebed deposits, from the fossilized remnants of animals whose descendants no longer exist in this region. The story it tells is this: 10 to 15,000 years ago, much of what is now the Gobi was alive. Rivers ran through it. Not seasonal streams that vanish in the dry months, but permanent waterways feeding lakes that persisted year-round. The pollen record shows grasslands where today there is only rock and sand, dense, productive grasslands capable of supporting large herds of grazing animals. Fossil deposits from this period reveal horses, gazelles, and large bovids moving through a landscape that would have looked, to any traveler arriving from the future, almost unrecognizable. Researchers have described it as a Central Asian equivalent of the Green Sahara, that well-documented period when the Sahara Desert itself was verdant and inhabited, before climate shifts turned it into the wasteland it is today. These are not speculative reconstructions. They are published findings from peer-reviewed research conducted by Chinese, Mongolian, and international teams working in collaboration across a region that has only relatively recently opened to systematic scientific investigation. The evidence is in the sediment. It is in the pollen. It is in the bones. And if the land was alive, then people were almost certainly in it. Early humans are not creatures who avoid productive landscapes. They follow water. They follow herds. They establish themselves wherever the environment offers enough to sustain a community, and the pre-desert Gobi offered considerably more than enough. The same migration corridors that brought early populations deep into the heart of Asia during the late Paleolithic would have funneled people into this region, where they would have found rivers, game, and the kind of reliable resource base that supports not just survival, but something approaching permanence. They would have had fires, hearths, communities organized around the rhythms of a landscape that rewarded knowledge of it. They would have learned the seasonal patterns of the rivers, the migration routes of the animals, the locations of the freshwater sources that made life in this vast interior possible. They were, in the truest sense, at home. And then the world they knew ended. Not slowly, not in the way that climates shift across generations, giving people time to adapt and move and find new strategies for living. The transition from the green Gobi to something approaching its present desolation appears, in the sediment record, to have been remarkably abrupt. The pollen record changes. The river deposits thin and disappear. The lake levels drop, the animals leave or vanish, and over the surface of a landscape that had been productive and inhabited, the sand begins to accumulate. Beneath that sand, preserved in sealed sediment layers, lie the records of everything that was here before, the seeds of plants that no longer grow in this region, the bones of animals that no longer walk it, and, in certain layers, the glass. The question that the sediment record raises quietly, without comment, simply by arranging its layers in the order they were deposited, is this: what happened between the living world and the silent one? What process, operating on what timescale, could have ended a green and inhabited landscape and replaced it with glass? Before writing, there was story. And before story was entertainment, it was something more essential. It was the technology by which a community preserved the knowledge it could not afford to lose. The human brain is not well designed for the direct transmission of information across deep time. We forget. Our children forget what we forgot. The specific details of individual events dissolve within a few generations into vague tradition, and tradition blurs further into myth. And myth eventually becomes something that scholars file under the category of narrative imagination rather than historical record. This is the conventional view that mythology is poetry, not documentation. But a growing number of researchers in the field of cultural astronomy, and what is sometimes called archaeomythology, have been making a different argument. They propose that certain myths, particularly those describing catastrophic sky events, are not pure invention. They are compressed, encoded memories of real events, transmitted across generations in the most durable container that pre-literate societies possessed. The story told around the fire, night after night, year after year, for thousands of years. The mythological traditions of Central Asian cultures, Mongolian, Tibetan, Chinese, and early Turkic, contain descriptions that, when read through this lens, become quietly extraordinary. Mongolian oral traditions include accounts of a time when the sky burned, when the great lights of heaven fell toward the earth, and when the landscape was transformed overnight into something unrecognizable. Tibetan cosmological texts reference a primordial catastrophe in which the world was remade by fire, not human fire, but fire that came from above. Early Chinese mythological accounts describe a period called the Time of the Great Calamity, when the rivers ran backward and the sun moved strangely across the sky, and when whole peoples disappeared from the earth. None of these traditions uses the vocabulary of science. They have no word for comet, no concept of cosmic bombardment, no framework for understanding an airburst in terms of atmospheric physics. What they have is the image, the sky on fire, the land transformed, the silence that came after translated into the language that was available to them, the language of divine agency, of celestial warfare, of a world that angered something vast and was punished for it. The detail that researchers find most striking is not any individual tradition, but their convergence. These cultures developed independently. Their languages share no common root. Their cosmological frameworks are constructed from completely different materials. And yet, at some point in their deep past, all of them seem to be describing the same event, the same fire in the sky, the same sudden change in the land, the same world that ended and was replaced by a different, harder one. This convergence does not prove anything in the strict scientific sense. A shared myth is not geological evidence, but it raises a question that is difficult to dismiss. If multiple independent traditions, separated by thousands of miles and thousands of years, all describe a catastrophic sky event that transformed the landscape of Central Asia, what are the chances that all of them invented the same story from nothing? The Gobi Glass may be the physical record of that event. The myths may be the human record. Two types of archive, preserved by completely different mechanisms, pointing toward the same moment in time, a moment when the world that existed before became unrecognizable, and the people who survived, it spent the rest of their lives, and the lives of everyone who came after them, trying to explain what they had witnessed. The glass doesn't lie. Neither perhaps does the story. Every substance on Earth has a threshold, a point of transformation, beyond which it can no longer remain what it was. Water becomes steam, iron becomes liquid, carbon becomes diamond. These transformations are not magical. They are physical processes governed by temperature and pressure, operating according to rules that are consistent, measurable, and ancient. The rules do not change. What changes is what you apply them to, and with how much force. Sand becomes glass the same way water becomes steam. You push the temperature high enough, and the material reorganizes. The silicon dioxide that makes up ordinary sand has a melting point of roughly 1,700 degrees Celsius, a number that sounds abstract until you place it in context. The surface of a lava flow reaches temperatures of around 1,200 degrees Celsius at most. A lightning bolt generates temperatures of approximately 30,000 degrees Celsius, but only along a channel so thin and brief that its energy dissipates almost immediately. To fuse sand into glass across a wide area, you need something that generates extreme heat and sustains it or delivers it so suddenly and so intensely that the sand has no time to do anything but transform. Lightning manages this on a small scale. The glass tubes it produces fulgurites are fascinating objects, hollow, brittle, branching structures that preserve the exact path of the electrical discharge in glass. You can find them in sandy deserts and beaches worldwide. They are typically no wider than a human thumb. The largest confirmed fulgurite ever discovered measured a few meters in length. To produce a glass field covering hundreds of square kilometers would require a lightning storm of impossible scale, a scenario so far outside any known meteorological possibility that no serious researcher has ever proposed it. The mechanisms that can produce large-scale glass fields are therefore limited to a short list. Volcanic activity can do it, when lava flows over surfaces at sufficient temperature, or when pyroclastic events generate the right combination of heat and pressure. Meteor impacts can do it, when the kinetic energy of a cosmic object strikes the ground and releases heat so concentrated that the target rock and the impactor material both vaporize, some of which then refuses into glass as it falls back to Earth. And, more recently added to scientific consideration, atmospheric explosions of sufficient scale can do it, events in which a cosmic body detonates in the air rather than the ground, releasing its energy as a heat pulse so intense and so sudden that the surface below it fuses. Each mechanism leaves a different signature. Volcanic glass carries the chemical profile of the magma that produced its specific ratios of certain elements that tie it unmistakably to a particular type of geological system. Meteoritic glass carries traces of the impactor extraterrestrial elements like iridium and platinum, pressure-induced crystal deformations, and isotopic profiles that point off-world. Airburst glass is the newest category and the least well characterized, but researchers are developing diagnostic criteria based on the small number of candidate events that have been studied. The Gobi Glass has been subjected to each of these tests. Its chemical profile has been mapped. Its isotopic ratios have been measured. Its mineral inclusions have been catalogued. And the results, spread across multiple independent studies conducted by different teams using different analytical methods, have consistently produced the same unsatisfying result. The glass carries signatures from more than one category. It does not read cleanly. It does not resolve into a single neat explanation. It whispers in multiple directions at once, as if the event that created it was something that existing categories were not quite built to contain. The meteor impact hypothesis is where the mind naturally goes when confronted with a glass field in a desert. It is the obvious answer, clean, dramatic, and supported by genuine precedent. Cosmic objects hit the Earth. They carry enormous kinetic energy. When that energy is released against a sandy surface, it fuses the ground. This is not speculation. It has happened. The evidence is documented. The most frequently cited parallel is the Libyan desert glass field, found in the eastern Sahara in Egypt near the Libyan border. These are chunks of yellow-green glass, scattered across roughly 6,500 square kilometers of desert, some of them weighing several kilograms, formed approximately 29 million years ago. They are silica-rich, incredibly pure, and so beautiful that they were carved into decorative objects in ancient Egypt. A famous carved scarab found in Tutankhamun's tomb contains a piece of Libyan desert glass at its center. For decades, the consensus explanation for the Libyan glass was a large meteor impact. The heat, the scale, the silica composition, everything pointed in that direction. The Gobi glass, at first examination, seemed to follow the same pattern. A cosmic impact in the right location, at the right time, generating the right temperatures. Case closed, or nearly so. Then the researchers started looking more carefully. A meteor impact leaves specific physical evidence that is, in principle, unmistakable. The most reliable indicator is shocked quartz grains of the mineral quartz that have been subjected to pressures so extreme that they develop internal fracture planes called planar deformation features. These features only form at pressures achieved by cosmic impacts or nuclear explosions. They cannot be produced by volcanic activity or any ordinary geological process. If you find shocked quartz, you are in the vicinity of an impact. Researchers searching the Gobi glass deposits for shocked quartz found it in some samples, and in some locations. But the distribution was inconsistent. Not all glass zones showed the same pressure indicators. If a single large impact had created the entire glass field, you would expect the pressure signatures to follow a coherent pattern radiating from a central point. The Gobi Glass does not show this pattern. The signatures are distributed across a wide area in a way that suggests multiple events, or an event whose energy delivery was fundamentally different from a point source impact. More troubling was the search for the crater itself. A meteor impact capable of generating glass across hundreds of kilometers would be a major event. It would leave a crater at least several kilometers in diameter, and probably much larger. Craters of this size do not disappear. They persist in the geological record for millions of years. Researchers using satellite imaging, ground survey, and geological mapping have searched the Gobi region and its surroundings for a candidate crater with appropriate scale and appropriate age. Nothing has been found. The absence of a crater does not prove the absence of an impact. Some craters are buried, some are obscured by later geological activity, but the absence is a problem that the impact hypothesis must answer. And then the Libyan desert glass, the closest parallel, complicated everything further. In 2013, a research team analyzing the chemical composition of Libyan glass with new precision instruments published results, suggesting that the glass's origin was not a ground impact at all. The chemical profile, they argued, better matched a cosmic airburst, an explosion in the atmosphere rather than a contact with the ground. If the Libyan glass, which had been the gold standard reference for desert impact glass for decades, turned out to be airburst produced, then the entire interpretive framework for anomalous desert glass fields needed to be revisited. The meteor theory is not wrong. Something cosmic almost certainly produced the Gobi glass. The extraterrestrial signatures in the chemistry are too clear to dismiss. But the theory, in its simplest form, a single large rock hitting the ground at a single point, fails to account for what the glass actually shows. The impact, if there was one, was not ordinary, or there was no impact in the traditional sense at all. And if there was no impact in the traditional sense, then something else happened. Something that generated impact-level heat without impact-level contact, across a geographic area far too large for any simple collision to explain. The obvious answer had stopped being obvious. And science, when the obvious answer stops working, is forced to consider the uncomfortable ones. On the morning of the 30th of June 1908, the sky above a remote region of Siberia did something that had no precedent in recorded human experience. A cosmic object now understood to have been a fragment of a comet or asteroid, somewhere between 50 and 80 meters in diameter, entered Earth's atmosphere and exploded. Not on the ground, in the air, at an altitude of approximately 8 to 10 kilometers, with a force estimated at between 10 and 15 megatons of TNT. The explosion was heard 1,000 kilometers away. Windows shattered in towns hundreds of kilometers from the blast. The shockwave circled the Earth twice, and across roughly 2,000 square kilometers of Siberian forest, trees were knocked flat, all pointing outward from the explosion's epicenter like the spokes of a wheel, stripped of their branches, scorched by the heat pulse that preceded the shockwave by a fraction of a second. No crater was ever found, because nothing hit the ground. This event, the Tunguska explosion, is the best documented example of a cosmic airburst in history. It happened over a sparsely inhabited region, which is the only reason no human casualties were confirmed. Had it detonated over a city, it would have destroyed everything within a radius of several dozen kilometers. Had it arrived 30 years later, during the Second World War, it might have triggered a global conflict by being mistaken for a nuclear strike. And crucially, for the purposes of what happened in the Gobi, had Tunguska occurred over a desert composed of dry sand rather than a boreal forest, the heat pulse would have fused the surface. It would have produced glass. The airburst hypothesis for the Gobi glass proposes exactly this scenario, scaled up. Not a 50-meter object, but something considerably larger, or several objects arriving in proximity, exploding in the atmosphere above the Central Asian corridor, and delivering a heat pulse of sufficient intensity and duration to fuse the desert surface below without ever touching it. This model addresses the problems that the impact hypothesis cannot. It explains the absence of a crater, because there was no ground contact. It explains the distributed pattern of glass deposits because an airburst's heat envelope is elliptical and wide, not radial from a single point. And it explains the pressure signatures because an airburst generates significant overpressure in the shock wave, capable of producing some, but not all of the mineral deformation features that a full ground impact would create. The Younger Dryas impact hypothesis, which proposes that a fragmented comet produced multiple simultaneous airbursts across the northern hemisphere around 12,900 years ago, places this scenario in a global context. The Gobi Glass, under this framework, is not an isolated airburst above one desert. It is one of many surface expressions of a single catastrophic event that affected the entire planet. The North American continent showed it in wildfires. The ocean showed it in disrupted circulation. The climate showed it in the temperature crash that ended the warming period. And the Gobi showed it in glass. The question that follows from all of this, the question that is rarely asked directly but sits at the center of everything, is this. If an airburst of this scale, or a swarm of them, happened 12,900 years ago, why isn't it common knowledge? Why does the average person know more about the asteroid that killed the dinosaurs 66 million years ago than about a cosmic event that happened within the span of human memory? That is a question with an answer. And the answer is more interesting than the question itself. In 2007, a team of 26 researchers published a paper in the Proceedings of the National Academy of Sciences, proposing that a fragmented comet or asteroid impacted the Earth approximately 12,900 years ago, triggering the Younger Dryas cooling event and contributing to the extinction of North American megafauna and the disappearance of the Clovis culture. The lead author was Richard Firestone, a nuclear physicist from Lawrence Berkeley National Laboratory. The paper presented evidence from 24 sites across North America, describing a layer of extraterrestrial markers, nanodiamonds, magnetic microspherules, carbon spherules, and elevated platinum and iridium concentrations, all deposited at the same stratigraphic level, all dating to the Younger Dryas boundary. The scientific response was swift, intense, and largely hostile. Within months, papers appeared challenging the methodology. Researchers questioned the identification of the nanodiamond forms. They disputed the dating of the markers. They argued that the proposed evidence could be explained by existing geological processes without invoking a cosmic impact. The Firestone team responded. The critics responded to the response. The debate moved into the journals and the conference rooms, and the informal conversations of researchers who had opinions about it and were not shy about expressing them. This kind of controversy is not unusual in science. Ideas that challenge existing frameworks always face resistance. This is not a conspiracy. It is how knowledge progresses. Extraordinary claims require extraordinary evidence, and the YDIH was making claims that were, by any measure, extraordinary. It was asking multiple scientific disciplines to accept that a cosmic event on a scale not seen since the Chicxulub impactor that ended the dinosaurs had occurred within the span of human memory, at a time when human beings were already scattered across the northern hemisphere, and that this event had shaped the course of human history in ways that conventional archaeology had completely missed. The resistance, however, was not purely about evidence. There was a cultural dimension to it, a legacy of scientific overcorrection from the 19th and early 20th centuries, when catastrophism in geology had been associated with religious creationism and later with sensationalist popular science. The scientific mainstream had spent decades establishing the principle of uniformitarianism, the idea that Earth's history is shaped by gradual, consistent processes rather than sudden catastrophes, and that principle had become something closer to dogma than to methodology. Proposing a planetary-scale catastrophe within human history felt, to many researchers, like a step backward into a discredited tradition. But the evidence did not stop accumulating. Over the 15 years following the 2007 paper, studies supporting the YDIH were published from sites on 6 continents. The same stratigraphic layer, the same collection of extraterrestrial markers deposited at the same geological moment, was identified in Syria, in South Africa, in Chile, in the Netherlands, in South Korea. Each new site was independently analyzed by teams with no prior commitment to the hypothesis. Each new study found the same layer, the same markers, the same timestamp. The hypothesis's most vocal critics found their specific objections answered, one by one. The nanodiamond identifications were confirmed by additional techniques. The dating was refined and held. The proposed atmospheric mechanisms for continental wildfire and ice sheet disruption were modeled computationally and found to be consistent with known physical processes. The scientific consensus has not fully accepted the YDIH. The debate continues, in the way that genuinely important debates continue not because the evidence is absent, but because the implications are large enough to demand rigorous examination before acceptance. But the nature of the debate has changed. It is no longer a question of whether there is evidence for a Younger Dryas cosmic event. There clearly is. The question now is what that event looked like, how large it was, and what exactly it caused. This is how paradigms shift in science. Not with a single dramatic moment of acceptance, but with a long, slow accumulation of evidence that becomes increasingly difficult to set aside until one day someone looks back at the timeline and realizes the consensus has moved without anyone announcing that it did. There is a layer in the earth that tells a story in a single line. Dig down through the soil at hundreds of sites across North America, Europe, the Middle East, and parts of Asia sites that have nothing in common except their geography and the accident of their preservation, and at a certain depth you will find it. A dark band, thin and consistent, composed of compressed organic material and fine sediment, separating the layers above it from the layers below with the unmistakable clarity of a boundary. Above this layer, in the strata that represent the world after, different animals, different tools, different everything. Below it, the world that existed before, rich, complex, populated by creatures that no longer walk the earth. Archaeologists call this the black mat. It appears at Clovis sites across North America, the sites associated with the first well-documented human culture on the continent. At every Clovis site that has been excavated with sufficient care, the story is the same. Below the black mat, Clovis artifacts and the bones of mammoths. Above it, nothing. No mammoths. No Clovis tools. A complete and apparently instantaneous transition from one world to another, marked by a thin, dark line in the sediment. What the black mat contains is more interesting than what surrounds it. When researchers began analyzing this layer with the tools available to 21st century geochemistry, they found things that sediment formed by gradual accumulation should not contain. Microscopic diamonds, specifically a form called lonsdaleite, a hexagonal crystal structure that forms under the extreme shock pressures produced by cosmic impacts and is not known to occur naturally through any other process. Tiny spheres of melted iron and glass, called microspherules, that form when material is vaporized at extreme temperature and then re-solidifies in freefall through the atmosphere. Elevated concentrations of iridium and platinum elements that are rare in Earth's surface rocks, but common in comets and asteroids, and that appear in anomalously high concentrations at exactly one other globally recognized stratigraphic boundary, the KPG boundary, the layer that marks the Chicxulub impact and the end of the dinosaurs. Every one of these markers is independently recognized as an indicator of cosmic bombardment. Finding one of them at a single site could be a coincidence. Finding all of them together, at the same stratigraphic level, at sites distributed across an entire hemisphere, removes coincidence from the conversation entirely. The black mat is a crime scene. Every detail it contains points toward the same event, an event violent enough to deposit cosmic material across an entire hemisphere simultaneously, intense enough to leave mineralogical signatures that can only form under pressures exceeding anything the normal geological world produces, and sudden enough to appear as a line rather than a gradient in the sediment record. The most striking aspect of the black mat is not its chemistry, it is its geographic distribution. The same layer, identifiable by the same chemical profile, appears at sites that span thousands of miles. The timing, established by multiple independent dating methods, is consistent across all of them. Whatever deposited this layer did not do so gradually, in different places at different times. It did it everywhere, essentially at once. The mathematics of this distribution are not complicated. For a single, uniform chemical signature to appear simultaneously across multiple continents, the mechanism must be capable of operating at a planetary scale. A localized impact cannot do this. A single volcano cannot do this. An ocean circulation shift cannot do this. The only mechanisms that can distribute material across a hemisphere in a single event are atmospheric, something that goes into the atmosphere and comes down everywhere at once. The black mat is a timestamp. Its message is simple and legible in the language of geochemistry. Something came from outside the Earth, approximately 12,900 years ago, and left its mark on the soil of an entire hemisphere. The world that existed below this line was different from the world that existed above it. Something ended one and began the other. The glass in the Gobi was formed in the same window of time. The same fire that wrote the black mat may have written the desert. Every investigation eventually arrives at the moment when individual pieces of evidence must be set beside one another to see if they fit. The Gobi Glass is a piece of evidence. The black mat is a piece of evidence. The Younger Dryas climate crash is a piece of evidence. The mythological traditions of Central Asian cultures are a piece of evidence. The sediment record that shows the green Gobi becoming the barren Gobi within what appears to have been a relatively short period of time is a piece of evidence. The question is whether these pieces form a picture or whether they remain scattered, suggestive but unconnected. Dating the Gobi Glass is technically demanding. The primary methods available for glass formation events, thermoluminescence dating, and optically stimulated luminescence work by measuring accumulated radiation damage in the glass lattice, estimating how long the material has been shielded from sunlight since it was last heated to extreme temperatures. These methods have margins of error that, in absolute terms, span thousands of years. They are not precise enough to say with certainty that the Gobi Glass formed in exactly the same decade as the Younger Dryas onset. What they can say, across multiple independent analyses, is that the glass formed within a broad time range that is broadly consistent with the Younger Dryas boundary. Researchers examining Gobi Glass samples specifically for YDIH markers have produced results that range from strongly suggestive to inconclusive. Some samples show elevated platinum group element concentrations consistent with cosmic input. Some contain microscopic carbon forms that are associated with high-temperature combustion events of unusual scale. Some show mineralogical signatures consistent with the pressure environment of an airburst rather than a volcanic origin. None of these findings, individually, constitutes proof. Together, they form a pattern. Geography adds weight to the pattern. The proposed trajectory of the Younger Dryas impactor, a fragmented comet arriving from a particular quadrant of the inner solar system, entering the atmosphere at a shallow angle and breaking apart across the northern hemisphere, places the Gobi Desert directly within the impact corridor's reach. Researchers modeling the geographic distribution of YDIH effects have noted that Central Asia is one of the regions where a major airburst would be expected to have surface-level consequences. The Gobi is not a peripheral location in this model. It is close to the center of the predicted impact zone. The honest summary of where the evidence stands is this. The connection between the Gobi Glass and the Younger Dryas impact hypothesis is a working hypothesis, not a settled conclusion. The dating is consistent but not precise enough to be definitive. The chemical markers are suggestive but not unambiguous. The geographic positioning is compelling but not confirmatory. And yet, the alternative that the Gobi Glass formed independently of the largest cosmic event in human prehistory through some unknown mechanism, in a location that happens to sit at the center of the event's predicted impact corridor, at a time that happens to fall within the event's chronological window, requires a degree of coincidence that becomes increasingly difficult to accept the more carefully you examine it. The glass is in the desert. The desert sits in the path. The path leads back to an event that reshaped the planet. Whether the connection is direct or circumstantial, it is telling the same story from a different angle. And the story, whichever angle you read it from, keeps pointing toward the same moment, the same fire, the same sky, the same ground, turning to glass beneath a heat that had no earthly source. The desert, in our imagination, is empty. It always has been. We assume a place too harsh for permanent habitation, too punishing for anything more than the occasional passing traveler moving quickly between more forgiving places. This assumption feels natural. It feels logical. And it is, for the Gobi as it exists today, largely accurate. But the Gobi that existed 12,000 years ago was not today's Gobi. And the people of 12,000 years ago were not absent from it. The ancient DNA revolution, the extraordinary proliferation of genetic studies conducted on prehistoric human remains since the sequencing of the first ancient genome in 2010, has transformed our understanding of who lived where and when and in what numbers. across the vast prehistoric interior of the Eurasian continent. What was once inferred from the distribution of stone tools and the locations of known excavation sites has been cross-referenced against a genetic map that now includes thousands of ancient individuals from across Europe and Asia. The picture that has emerged is one of far greater human presence and far greater movement than previous models predicted. Central Asia, in the late Paleolithic and early Mesolithic, the period spanning roughly 15,000 to 10,000 years ago, was not the empty corridor between more populated regions. It was a populated region in its own right, inhabited by human communities whose genetic profiles show complex histories of movement, mixing, and long-term residence. These were not transient populations passing through. The genetic diversity of ancient Central Asian samples suggests communities that had been in the region long enough to develop distinct local lineages, people whose connection to this landscape was not incidental but deep. In and around the Gobi region specifically, archaeological evidence of late Paleolithic habitation has been accumulating for decades, though the scale of excavation work remains modest relative to the territory's size. Sites dated to the relevant period show stone tool assemblages characteristic of the microlithic traditions common across Central and East Asia at this time. Small, finely worked blades and points designed for the kind of versatile, mobile hunting that a productive grassland environment would support. Hearth sites, the most direct evidence of human presence. The places where people gathered around fire have been found and dated. Middens, the archaeological name for the accumulated debris of daily life, show the bones of the animals these people ate. Horses, gazelles, deer, and species that no longer live in this region. These were not primitive beings in the pejorative sense of that word. They were fully modern humans, as cognitively capable as any person alive today, equipped with the accumulated knowledge of communities that had been adapting to and thriving in this environment for generations. They knew this landscape the way you know your own neighborhood, its rhythms, its resources, its dangers, its seasonal patterns. They were, by any reasonable measure, at home. The glass fields that now lie buried beneath the Gobi surface are distributed across exactly the same regions where evidence of prehistoric habitation has been found. This is not a coincidence that can be easily explained by reference to site selection bias in archaeological work. The glass deposits and the human occupation sites both appear to concentrate in the areas that would have been most productive during the Green Gobi period, the areas near ancient waterways and lake shores where resources were richest. If the glass was formed by a heat event, by an airburst or a series of airbursts reaching the surface of the Gobi with temperatures sufficient to fuse sand, then the people living in those productive zones were there when it happened. Not some of them, in some hypothetical scenario. The people whose hearth ashes and tool scatters and animal bones are preserved in those sediment layers were standing on ground that was about to become glass. There is a particular kind of absence in archaeology that speaks more loudly than presence. Archaeologists are trained to read what they find. The bones, the tools, the charcoal, the pottery, the remnants of structures, these are the materials of the discipline, the vocabulary in which the past communicates with the present. But there is a secondary vocabulary, less often discussed, that belongs to what is not found, the sudden end of a habitation sequence, the stratigraphic layer that contains occupation evidence and then, without transition, gives way to sterile sediment, sediment that was deposited by wind or water, with no human material mixed into it. Archaeologists call this settlement discontinuity, and it is precisely what it sounds like. The human record in a location simply stops. Settlement discontinuity can be explained in several ways. A community moved, choosing voluntarily to establish itself somewhere more favorable. A resource base shifted, making the location less viable and encouraging relocation. Conflict drove people out. Environmental change made the area temporarily uninhabitable. In most cases, settlement discontinuity is followed, eventually, by renewed occupation. Different people, different tools, different cultural traditions, often separated from the previous occupation by a gap of centuries. In the Gobi region, around the Younger Dryas boundary, researchers have documented exactly this pattern at several excavated sites. Habitation layers, rich with the evidence of active community life, end abruptly. The stratigraphy above them contains no human material. Then, after a gap, sometimes a gap of several centuries, sometimes more evidence of new occupation appears, But the new occupants are different. Their tools are made differently. Their resource use patterns are different. The genetic material from their remains, where it has been analyzed, shows population composition that differs from the pre-gap occupation. This is not gradual evolution. This is not a smooth cultural transition. This is a before and an after, separated by silence. The silence in the sediment is not unique to the Gobi. Across Central Asia broadly, the Younger Dryas boundary in the archaeological record shows the same pattern: occupation, silence, then eventual reoccupation by populations that appear to have arrived from elsewhere or to have been reconstituted from a much smaller surviving group. Ancient DNA studies have identified what geneticists call population bottlenecks moments in the past, when the breeding population of a lineage was drastically reduced, leaving a genetic signature of reduced diversity in the descendants. Several Central Asian lineages show bottleneck signatures dating to the Younger Dryas period. A population bottleneck in genetics is the mirror image of the settlement discontinuity in archaeology. One tells you that fewer people survived. The other tells you that the places they had lived became empty. Together, they tell you that something happened to the people of this region during this period. Something that killed large numbers of them, scattered the survivors, and left the landscape empty long enough for the wind to deposit clean sediment over the traces of their lives. The glass fields are dated to the same period. The silence in the sediment sits in the same stratigraphic window as the glass. The glass and the silence are neighbors in time, separated by nothing more than the difference between the moment of formation and the moment of absence. And then there are the details that the sediment preserves, without comment, without context, without any frame of narrative, just material, arranged in layers, saying what happened without saying what it meant. Among the fragmentary remains at pre-Dryas Gobi habitation sites, the small bones of children, the worn edges of tools used by hands that had done this work for years, the particular accumulation of hearth ash that comes from fires tended through many seasons. These are the traces of families, of ordinary, continuous, rooted human life. Above the glass layer, above the horizon where the settlement discontinuity begins, nothing. There is no way to know from the evidence available what the final moments of these communities looked like. But the sediment knows that there was a before and an after. The silence between them is real. And whatever filled that silence was not gradual. Catastrophe does not simply end things. It reshapes them. The fire that destroys a forest also seeds the next one. The flood that erases a settlement also disperses its people across the landscape, carrying fragments of what they knew into places that had not known it before. Everyone in the Gobi died. The evidence makes this clear not because survival is the optimistic assumption, but because the genetic and linguistic record that follows the Younger Dryas period shows populations that descended from somewhere, and that somewhere points back towards Central Asia. Survival was not universal. It was not comfortable, but it happened, and what the survivors did with what they carried forward may be one of the most consequential acts in the history of our species. The concept of the catastrophe survivor as cultural transmitter is not a romantic invention. It is grounded in how human communities actually behave in the aftermath of devastating events. The survivors of a catastrophe are not blank. They carry knowledge, practical knowledge of how to find water, how to identify edible plants, how to make tools from available stone, but they also carry memory. The specific, vivid, unshakable memory of what they witnessed. And in cultures without writing, that memory becomes the most important thing a person can pass on. It becomes story. The linguistic evidence for post-Dryas population movement out of Central Asia is among the most striking and least discussed aspects of this entire subject. Historical linguists have long recognized that Central Asia is the origin point for an extraordinary proportion of the world's major language families. The proto-language that would eventually diversify into the Sino-Tibetan family encompassing Mandarin, Tibetan, Burmese, and hundreds of related languages, appears to have its roots in or near the Gobi region. The Altaic hypothesis, while contested, proposes a common ancestral language connecting Mongolian, Turkic, and possibly Korean and Japanese. The origins of the Indo-European family, which includes nearly half of all human languages spoken today, have been traced through genetic and linguistic analysis to a steppe population in Central and Western Asia. These are not fringe claims. They represent the mainstream of historical linguistics, supported by decades of comparative analysis, and increasingly confirmed by ancient DNA research that maps the movement of populations carrying specific language families across the continent. The convergence is not subtle. The same geographic region that shows evidence of a catastrophic heat event during the Younger Dryas is also the region that appears to be the origin point for language families spoken today by billions of people. The same period that shows population collapse in the archaeological and genetic record is also the period after which human populations begin dispersing outward from Central Asia in the patterns that historical linguistics documents. The survivors moved. They carried their genes and their languages and their stories. And their stories, as Chapter 2 showed, all describe the same event. The fire in the sky. The world that ended. The land that changed. What is extraordinary about this transmission is its durability. The story traveled with the people who carried it, was told to children who told it to their children, was translated from one language into another as populations diverged and languages split, was transformed from factual account into sacred narrative and eventually into myth. And it still arrived, recognizable, in multiple independent traditions, describing the same catastrophic sky event over the same Central Asian landscape. The Gobi Glass is the physical record of that event, the mark it left on the ground. The myths are the human record, the mark it left on the mind. Both forms of record have been waiting, in parallel, for someone to read them together. The glass has been in the desert for 12,000 years. The myths have been in the cultures for just as long. They are, in the deepest sense, the same document. Every generation of archaeologists inherits a timeline. It is drawn with the confidence of accumulated evidence here. Agriculture begins. Here, the first cities appear. Here, writing is invented. Here, the modern world takes its first recognizable shape. The timeline is not invented. It is built from real excavations, real artifacts, real dates. It is the most honest account of human history that the available evidence supports. The problem is that the available evidence is a vanishingly small fraction of what once existed. Consider the conditions required for an archaeological site to survive to the present. The materials must be durable stone, ceramic, bone, metal. The site must be buried quickly enough to be protected from surface erosion, but not so quickly or deeply that it remains inaccessible. The burial environment must be chemically stable enough to prevent decomposition. The site must not be destroyed by subsequent human construction, agricultural activity, or geological events. And it must, eventually, be found, which requires that someone looks in the right place with the right methods at the right time. Most of human prehistory does not meet these conditions. Most of it is gone dissolved by time, crushed by subsequent events, buried under landscapes that have never been surveyed. The timeline we have is built from the fraction of a fraction of a fraction of the human story that happened to survive and happened to be found. This is not a reason to abandon the timeline. It is a reason to hold it with appropriate humility, to recognize it as a minimum bound on human achievement rather than an accurate ceiling. In the last 2 decades, that minimum bound has been pushed backward repeatedly by discoveries that the existing timeline did not predict. Göbekli Tepe, in southern Turkey, was excavated beginning in 1994 and revealed a complex of massive carved stone pillars, arranged in circles, decorated with detailed animal reliefs, and dated to approximately 12,000 years ago. It predates Stonehenge by 7,000 years. It predates the supposed invention of agriculture and settled society. Its construction required organized labor, planning, specialized skill, and a level of social coordination that the conventional model of hunter-gatherer society in this period did not account for. Göbekli Tepe was not built by an anomalous genius working alone. It was built by a community organized enough to quarry and transport multi-ton stones, skilled enough to carve them with precision, and motivated by something powerful enough to sustain the effort across generations. Whatever that community was, it was not the primitive, unorganized, wandering band of foragers that the conventional timeline had placed at this period in human history. The Gunung Padang site in Indonesia has produced dating results contested but published in peer-reviewed form, suggesting construction activity extending back as far as 25,000 years ago. The Sangxingdui culture in China produced bronze artifacts of extraordinary sophistication at dates far earlier than Chinese civilization was supposed to have developed metallurgy. Every few years, another site, another finding, another quiet revision to the timeline. None of this proves the existence of a lost advanced civilization with technology comparable to the modern world. That claim goes far beyond what the evidence supports. And this documentary has no interest in going beyond the evidence. What it does prove is something more modest and more genuinely significant. The conventional timeline of human cognitive and social development is a minimum estimate, not an accurate one, and the further back we look, the more we find that human beings were doing things we did not expect them to be doing. The Gobi region, one of the least excavated large territories on Earth, sits at the center of this question. What was there? What developed there? And what did the glass consume? The Gobi Desert covers approximately 1.3 million square kilometers. To put that in perspective, it is larger than Peru, larger than South Africa, larger than every country in Western Europe except Russia. It spans parts of northern China and southern Mongolia, encompassing multiple distinct geological zones, the rocky desert pavements of the Mongolian plateau, the sand dune fields of the Badan-Jaran, the ancient lake basin of the Tarim. It is not a uniform landscape. It is a continent within a continent. The total area of the Gobi that has been subjected to systematic archaeological survey, the kind of methodical, grid-based, surface collection and subsurface testing work that would allow researchers to say with confidence what is or isn't, there is a small fraction of its total extent, a very small fraction. The combination of extreme terrain, remoteness from logistics infrastructure, funding limitations, and political complexity, the Gobi straddles an international border between China and Mongolia, with access governed by different institutional and governmental frameworks on each side, has meant that most of this vast territory has been walked across but not investigated. What limited survey work has been done is suggestive in exactly the way that partial information is suggestive. It shows enough to make the unseen portion tantalizing. Known but unexcavated sites exist across the Gobi region, locations identified through surface finds, satellite imagery, or brief reconnaissance visits, but not followed up with the systematic excavation that would reveal their full extent and chronology. Ancient dried riverbeds, identifiable through remote sensing as topographic features, even where they no longer carry water, trace the corridors along which prehistoric populations would have moved and settled. Where these corridors have been investigated, human occupation evidence consistently appears. The technology now exists to see beneath desert surfaces without excavation. LiDAR light detection and ranging uses pulsed laser measurements from aircraft or satellites to generate extraordinarily detailed topographic maps, revealing buried structures and surface features invisible to the naked eye. It was LiDAR that, in 2012, revealed the full extent of the medieval Khmer city of Mahendraparvata in Cambodia, showing a metropolis several times larger than researchers had previously known, hidden for centuries beneath jungle canopy. Similar applications in Central America have revealed Maya cities of comparable scale. The same technology has been applied, more recently, to desert environments, and researchers working in the broader Central Asian region have described their preliminary findings in the careful, understated language of scientists who have seen something they are not yet ready to fully claim. There is a specific geographic detail worth noting. In several regions of the Gobi where glass deposits have been identified at the surface, associated surveys have found prehistoric tool scatters in the same zones, stone artifacts of the type and period consistent with late Paleolithic occupation, lying on or near the surface in areas where wind erosion has stripped away the covering sediment. The glass and the tools are neighbors in space as well as in time. They occupy the same ground. This creates a scenario that is both scientifically intriguing and practically urgent. If the glass formed in a heat event that also affected the human populations living in those zones, then the stratigraphy beneath the glass fields may contain exactly what researchers need to understand both the event and its human consequences, occupation layers, organic material for dating, and possibly cultural remains that could illuminate what kind of community existed here before the transformation. The glass fields may, in other words, be lying directly on top of the evidence that explains them. The concept of palimpsest archaeology, the recognition that desert surfaces are layered documents, with multiple periods of human activity compressed into the same physical space by the erosive processes that remove intervening sediment, makes this a genuine research priority rather than a speculative hope. The Gobi is not empty. It has not been read. These are different things, and the difference matters enormously for what we think we know about the world that existed before the glass. There is a question that no one asks directly in the academic literature on prehistoric catastrophism, but that sits beneath the surface of every serious treatment of the subject. Did the people who lived through these events have any warning? The intuitive answer is no. Prehistoric people, the assumption goes, lacked the astronomical knowledge to track cosmic objects, lacked the communication networks to disseminate warnings even if they had them, and lacked the technological capacity to do anything about an incoming threat, even if it had been identified. The sky fell without warning, and it found people unprepared. This assumption may be wrong, not in the dramatic, cinematic sense of a prehistoric civilization with telescopes and evacuation plans, but in a more subtle and more interesting sense. Prehistoric astronomy was more sophisticated than the conventional timeline acknowledges. This is no longer seriously disputed. The solar and lunar alignments at Stonehenge, constructed beginning approximately 5,000 years ago, demonstrate a precise and multi-generational commitment to tracking the movements of celestial objects. The Nebra sky disk, a bronze artifact found in Germany and dated to approximately 3,600 years ago, shows a level of astronomical representation, a specific configuration of the Pleiades and Moon that implies systematic sky observation across generations. At sites worldwide, prehistoric structures encode astronomical alignments so precise that they could only have been produced by communities that had been watching the sky carefully, consistently, and collectively for centuries or millennia. The Younger Dryas comet, in the scenario proposed by the YDIH, would not have arrived without any warning visible to an attentive skywatcher. A fragmenting comet on an Earth-crossing trajectory would have been observable for months before its closest approach. A brightening object in the night sky, moving in ways that distinguished it from stars, growing more prominent over weeks. Any community that watched the sky regularly would have noticed it. Whether they could have understood what they were seeing is a different question. Without a conceptual framework for comets and orbital mechanics, a brightening sky object would have been interpreted in the only frameworks available as a divine message, an omen, a celestial being with intentions. The specific nature of those intentions would have been read from context: the object's brightness, its movement, its association with other celestial events. In the Gobi region and surrounding areas, rock art and cave painting traditions from the late Paleolithic include representations of sky objects that do not correspond to the sun, moon, or any star in its normal position. Some of these elongated forms with trails, radiating shapes, objects descending toward the horizon, have been interpreted by researchers studying prehistoric astronomical iconography as possible, representations of cometary or meteoric events. These interpretations are contested, as all interpretations of prehistoric art necessarily are. But the temporal distribution of such depictions shows a notable concentration in the period approaching the Younger Dryas boundary. The image that emerges from this thread of evidence, tentative, contested, but genuinely compelling, is of communities watching a growing light in the sky over a period of months, incorporating it into their ritual and artistic practice, understanding it as something significant, something that demanded attention and ceremony, and perhaps fear, without any framework that could have told them what it was or what it would do. They were watching. They were aware. They encoded what they saw into the oldest form of record available to them. And then the light they were watching did what lights of that kind do. It arrived. Science is a human enterprise. This seems obvious, but it is frequently forgotten in the way science is discussed, as though discoveries arrive through the impersonal operation of methodology rather than through the specific choices, ambitions, frustrations, and persistence of individual people working in difficult conditions with imperfect tools. The researchers who study the Gobi Glass are not a single community. They are scattered across institutions in China, Mongolia, Russia, Germany, the United States, and several other countries, connected by correspondence and occasional collaboration, divided by different theoretical commitments and methodological preferences, and united by the fact that they have chosen to spend significant portions of their professional lives on a question that has not yielded a clean answer. Chinese geological institutions have been the most active in physical surveying of the Gobi Glass deposits, for the obvious reason that a large portion of the Gobi lies within China's borders, and access requires Chinese institutional involvement. Their contributions to the basic mapping of glass deposit locations, extent, and surface distribution are foundational to everything else. Mongolian researchers have contributed site documentation from the northern Gobi and the associated steppe transition zones. Russian geochemists, drawing on deep institutional traditions in isotope geochemistry developed during the Soviet period, have contributed some of the most detailed chemical analyses of Gobi Glass samples. European and American researchers have primarily engaged with the material through the lens of the YDIH, bringing the Gobi evidence into the broader framework of the global Younger Dryas investigation. The funding landscape for this research is, to put it generously, challenging. The Gobi Glass investigation sits at the intersection of multiple disciplines: geology, geochemistry, archaeology, climatology, astronomy, and falls cleanly within none of them, which makes it difficult to fit into the standard funding categories of any single discipline. Researchers pursuing this question frequently do so as an adjunct to other funded projects, using equipment time and sample analysis budgets that were allocated for related work. This is not unusual in science, but it does limit the pace and scale of investigation. What is perhaps most striking about the community working on this problem is the professional courage that serious engagement with it requires. The YDIH remains controversial. Researchers who publish findings consistent with a cosmic origin for the Gobi Glass, or who cite the YDIH framework in their interpretations, risk being associated in reviewers' minds with the fringe end of the field, even when their methods are impeccable and their findings are reproducible. The most cautious researchers describe the anomalous results they find in language that carefully avoids committing to any specific interpretive framework, reporting measurements without claiming what the measurements mean. This is not dishonesty. It is the rational response of a scientist who has watched colleagues take reputational damage for being too willing to follow anomalous evidence toward uncomfortable conclusions. The researchers who have chosen to engage more directly with the implications, who have published interpretive papers arguing for a cosmic origin, who have placed their Gobi findings within the YDIH framework, who have been willing to say in print what the evidence suggests, are a smaller group. Their papers attract citations from both directions, from researchers building the case for the hypothesis and from researchers working to refute it. Both kinds of attention are, in the long run, what advances understanding. 20 years of publication, dozens of studies. The question is still open. In science, that is not a failure of the researchers. It is a measure of the question's genuine difficulty and, perhaps, of its genuine importance. Every scientific investigation produces two kinds of findings: results that fit the existing framework and results that don't. The first kind gets published with relative ease. The second kind gets published slowly, reluctantly, carefully hedged, because presenting an anomaly to a scientific community that has built its understanding on the existing framework is an act of methodological courage, with real professional stakes attached to it. The Gobi Glass investigation has produced an accumulation of anomalous findings that, individually, can be absorbed and explained away. Collectively, they form a pattern of stubborn non-conformity that serious researchers find impossible to ignore. The distribution pattern is the starting point. If the Gobi Glass was produced by a single large impact, it should be distributed in a pattern consistent with impact physics, concentrated near the central impact point, thinning out radially as distance from the source increases, with specific orientation patterns in the elongated glass forms reflecting the angle of the incoming projectile. The Gobi Glass does not show this pattern. The deposits are distributed in multiple discrete zones across a wide geographic corridor, with roughly comparable concentrations in areas separated by many kilometers of glass-free terrain. This distribution is more consistent with multiple events, or with the irregular heat footprint of an airburst, than with the radial dispersal of a single ground impact. The temperature indicators embedded within the glass add another layer of anomaly. Different regions of the glass field show evidence of formation temperatures that vary significantly. Some zones formed at temperatures consistent with the lower end of what a large airburst would generate, Others show evidence of far more extreme heating. If a single event created all the glass, this variation requires an explanation. If multiple events created it, a swarm of air bursts arriving across a wide area, the variation becomes expected. The pressure signatures are perhaps the most technically complex anomaly. Some glass samples contain high-pressure mineral phases, forms of silica that only crystallize under pressures far exceeding anything that the Earth's surface generates through normal geological activity. These phases are well documented as products of hypervelocity impact events. Their presence in the Gobi Glass points unambiguously toward a high-energy cosmic event. But their distribution within the glass field is uneven. Not all zones contain them, and the zones where they appear do not form the coherent pattern that a single impact would generate. High-pressure phases, concentrated in multiple disconnected locations, suggest multiple energy delivery points, not one. The isotopic profiles carry their own strangeness. The ratio of oxygen isotopes in a glass sample is a reliable indicator of its origin environment. Each geological and cosmic source has a characteristic ratio that serves as a fingerprint. The Gobi Glass samples that have been analyzed for oxygen isotopes show profiles that mix terrestrial and extraterrestrial signatures in proportions that are not consistent with any single known origin. They look like a blend, as if the material that became glass was partly from the Earth and partly from somewhere else, mixed at high temperature in an event that involved both. This is consistent with an airburst scenario, where a cosmic object vaporizes in the atmosphere and its material intermingles with the vaporized surface material below. But the specific ratios don't match the limited number of confirmed airburst events in the database. And then there is the absence. Researchers searching for the source crater, the ground-level impact structure that should exist if any part of the Gobi Glass was produced by a contact impact, have consistently found nothing of appropriate scale and age. This is not for lack of trying. Satellite surveys have been conducted. Ground surveys have mapped the geological structure of the region in detail. The crater is not there. Absence of evidence is not always evidence of absence, but in this case, the search has been thorough enough that the absence is itself an anomaly, one more data point that the simple impact model cannot accommodate. The Gobi Glass is a message written in a language that existing scientific categories can only partially read. The anomalies are not noise, they are the signal. And the signal, frustratingly, keeps pointing towards something that the current framework does not have a complete name for. When the existing models stop working, science does not stop. It builds new ones. The recognition that the Gobi Glass, and several other anomalous glass fields around the world, cannot be fully explained by either the standard impact model or any known volcanic mechanism, has motivated a small but growing community of researchers to develop theoretical frameworks capable of accommodating what the evidence actually shows. One such framework is the plasma vortex model, developed initially in the context of certain unexplained surface features in desert environments but increasingly applied to glass field formation. The model proposes that under specific atmospheric conditions, certain types of cosmic energy delivery, particularly the interaction between a superheated airburst fireball and the Earth's lower atmosphere, can generate rotating columns of plasma that descend toward the surface, move across it, delivering intense, concentrated heat to specific zones while leaving adjacent areas untouched. This model would explain the patchy, multi-zone distribution of glass deposits in a way that neither a point impact nor a simple airburst can. It predicts the kind of irregular, corridor-like glass distribution that the Gobi shows. Another emerging framework involves cometary airburst, clustering the idea that a fragmented comet, breaking apart during its final approach, delivers not a single explosion, but a sequence of explosions distributed along its trajectory over a period of seconds to minutes. Each fragment detonates at a slightly different point along the flight path, creating a linear or curvilinear series of airburst events whose combined heat footprint covers a vastly larger area than any single explosion could reach. Computer modeling of this scenario, using what is known about cometary fragmentation physics and atmospheric entry dynamics, produces surface effect patterns that show notable similarities to the Gobi Glass distribution. Neither model is established. Both are being developed through the iterative process that characterizes frontier science computational modeling, comparison with known events, search for confirmatory evidence in the field. They are not ready to be presented as conclusions. They are ready to be presented as serious possibilities being tested by serious researchers. The most important development in the Gobi Glass investigation over the coming decade may not come from the desert at all. As the catalogue of known comets and near-Earth asteroids grows, driven by planetary defense survey programs now conducting the most comprehensive sky surveys in human history, the database of known cosmic objects and their compositional profiles is expanding rapidly. When a cometary or asteroid composition profile is found that matches the extraterrestrial signatures in the Gobi Glass, the picture will clarify dramatically. The answer, when it comes, may arrive from above, from the same sky that sent the original question 12,000 years ago, still circling, still carrying the record of what it once did to a desert that has not forgotten. We live with a quiet assumption about the sky above us that it is, in its essential nature, safe. The sun rises and sets on schedule, the moon moves through its phases, the planets track their orbits with the precision of clockwork, the stars are fixed, or nearly so, in their patterns. The sky is not a source of danger, it is a backdrop. This assumption is understandable. It is even, in the context of a human lifetime, largely accurate. The probability of a significant cosmic impact during any individual's lifespan is very low. The sky, on the timescale of human experience, is stable. On the timescale of Earth's history, it is anything but. The geological record of Earth's surface contains more than 190 confirmed impact structures, craters, basins, and deformed geological formations left by cosmic objects that struck the planet with enough force to permanently alter the landscape. The largest of these are ancient. The Vredefort crater in South Africa, 2 billion years old, over 300 kilometers in diameter. The Sudbury Basin in Canada, 1.8 billion years old, originally perhaps 250 kilometers across. The Chicxulub structure in Mexico, 66 million years old, approximately 180 kilometers in diameter, the scar left by the object that ended the Cretaceous period and 75% of all species on Earth. But there are smaller, more recent structures as well. The Barringer crater in Arizona, approximately 1,200 meters across, formed roughly 50,000 years ago. The Manicouagan structure in Canada, 100 kilometers in diameter, formed approximately 215 million years ago. The Bosumptwi crater in Ghana, 10.5 kilometers across, formed 1 million years ago. Impact events are not rare in Earth's history. They are a regular feature of it. And these 190 confirmed structures represent only the impacts that left permanent geological signatures that have survived erosion, burial, and subsequent geological activity to the present. The actual frequency of significant cosmic encounters is higher, substantially higher. Researchers studying impact frequency estimate that objects capable of destroying an area the size of a large city strike the Earth, on average, approximately once per century. Objects capable of regional devastation, the Tunguska scale, arrive every few centuries. Events capable of civilizational disruption may occur on timescales of thousands of years. The 50,000-year gap between the last confirmed significant impact in the American Southwest and the present is not evidence that we are in a period of immunity. It is evidence that the timescales involved are long relative to recorded history, which creates a dangerous illusion of safety. The sky is not dangerous every day, but it is dangerous, in the way that all large, rare risks are dangerous, not constant, but inevitable on a long enough timeline. The Gobi Glass, in this context, is not an anomaly in Earth's history. It is a data point in a pattern. A planet that has been struck before, repeatedly, across its entire geological existence, was struck again within the span of human memory. The surprise is not that it happened. The surprise is that we have spent so long treating it as impossible. Every piece of glass in the Gobi is a reminder that the sky has no permanent commitment to leaving the ground alone. It did what it does, on a time scale we call prehistoric, only because no one was writing history when it happened. Someone, though, was watching. If the Gobi Glass were unique, the only anomalous glass field on Earth without a clear, conventional explanation, it would be easier to dismiss it as a localized curiosity awaiting a local explanation. But the Gobi Glass is not unique. It is one member of a family of anomalous glass fields, distributed across multiple continents, all of which share the same fundamental characteristic. They exist, they should not easily exist, and the explanations for them remain contested. The most famous is the Libyan desert glass, found in the eastern Sahara in a region straddling the Egyptian-Libyan border. Approximately 1,000 tons of yellowish-green glass are distributed across roughly 6,500 square kilometers of desert, in chunks ranging from small fragments to pieces weighing several kilograms. The glass is almost pure silicon dioxide, purer than most manufactured glass, and it formed at temperatures that most models place above 1,600 degrees Celsius. It is approximately 29 million years old. Researchers have proposed both a ground impact and an atmospheric airburst as its origin, with the airburst hypothesis gaining significant support from chemical analyses published in the past decade. No impact crater of appropriate size and age has ever been found in the region. A carved piece of Libyan desert glass sits at the center of a pectoral jewel found in Tutankhamun's tomb. Ancient Egyptians encountered this material, recognized its unusual qualities, its hardness, its translucency, its beauty, and incorporated it into sacred objects. They had no explanation for where it came from. They simply knew it was extraordinary. The Darwin glass field in Tasmania is another candidate, a collection of glassy material found in a remote part of western Tasmania, associated with a possible small impact, but with origin details that remain under investigation. The Wabar craters in Saudi Arabia, discovered in the 1930s, contain glass produced by a meteor impact dated to within the last few thousand years, making them among the most recent confirmed impact glass occurrences. And the Australasian tektite-strewn field is perhaps the most baffling of all. A distribution of impact glass covering an area from southern China through Southeast Asia, across the Indian Ocean, to southern Australia, representing one of the largest single glass-producing events known. It dates to approximately 790,000 years ago. Despite its size and the quality of the samples available for analysis, no source crater has ever been found. Not a trace. Not a candidate structure. Nothing. The absence of a confirmed crater for the Australasian tektite field has been a persistent mystery in impact geology for decades. An event capable of distributing glass across an area spanning thousands of kilometers in multiple directions would have to have been enormous. The resulting crater should be clearly visible in any geological survey of the region. That it has not been found despite active searching suggests either that it was formed in an unusual way that did not produce a typical crater morphology, or that it is buried under subsequent geological deposits, or that the tektite formation mechanism was different from what standard impact models predict. Each of these glass fields is its own mystery, but they share structural similarities, anomalous distribution, contested origin, absent or inadequate source craters that suggest they may be products of a mechanism or mechanisms that current geological models do not fully capture. The Gobi Glass is part of this family. It is one instance of a pattern that repeats, in different times and different places, across the planet's surface. Taken individually, each field is a puzzle. Taken together, they form a picture of a planet that has experienced cosmic energy delivery events of varying scale, distributed across its history, producing glass fields as the physical signature of encounters whose full nature is still being worked out. The Gobi is one entry in a global catalogue of cosmic events that left their marks on the ground. The catalogue is longer than most people know, and the entries in it are less well explained than the scientific literature's confident surface might suggest. The existence of planetary defense as a scientific and governmental priority is, in itself, a form of evidence. Governments do not allocate funding to protect against threats they consider hypothetical. The existence of NASA's Planetary Defense Coordination Office, established in 2016, and the European Space Agency's Parallel Planetary Defense Program, reflects a formal institutional acknowledgement that the risk of significant cosmic impact to Earth is real, finite, and worth preparing for. These programs are not fringe initiatives. They are mainstream, funded, staffed by credentialed researchers, and engaged in active operational work. In 2022, the DART mission, the Double Asteroid Redirection Test, successfully changed the orbit of a small asteroid called Dimorphos by deliberately crashing a spacecraft into it. It was the first time in human history that humanity had deliberately altered the trajectory of a natural cosmic body. The mission was conducted not as an experiment in abstract physics, but as a proof of concept for planetary defense, a demonstration that deflection technology can work, so that it will be available if it is ever needed. The implicit acknowledgement embedded in these programs is worth examining directly. The investment in planetary defense technology means that the scientific and governmental community accepts that the scenario the Gobi Glass may represent a cosmic event large enough to cause regional or civilizational damage is not just a historical curiosity, but a future possibility. The glass in the desert is evidence of what can happen. The DART spacecraft is evidence that we have decided it should not happen again without a response. There is one detail that the planetary defense conversation tends to underemphasize. The cosmic objects most difficult to detect and characterize are not solid rock asteroids, which are relatively bright and trackable, but cometary bodies, objects composed partly of ice and organic material, darker than rock, often approaching on trajectories that bring them into the inner solar system from unexpected directions with limited warning time. A fragmented comet, the type of object implicated in the Younger Dryas impact hypothesis, is particularly difficult to detect, because its fragmented state means that individual pieces may be too small to register on survey instruments until they are already dangerously close. The technology to provide reliable early warning for a Younger Dryas scale cometary event does not yet fully exist. Programs are under development, including the Vera Rubin Observatory's Legacy Survey of Space and Time, which will catalogue millions of solar system objects with unprecedented completeness. But the gap between current capability and full protection remains real. The Gobi Glass was formed in a world with no warning system, no response capability, and no framework for understanding what was happening. We have not yet closed all the distance between that world and full preparedness. What we have done is begin driven, in part, by the accumulating evidence that events like the one that wrote the desert in glass are real and are not permanently in the past. There is a particular comfort in believing that the story of human civilization is a story of continuous progress, a long, slow climb from simple origins toward increasing complexity, interrupted by setbacks and regressions but fundamentally directed upward, each generation building on what the one before it left behind. This narrative is not pure invention. It captures something real about the human experience. We do build. We do accumulate knowledge across generations. The world of the 21st century is, in material terms, dramatically more complex than the world of 10,000 years ago. But the Younger Dryas impact hypothesis, if accepted, complicates this narrative in a fundamental way. If a cosmic event approximately 12,900 years ago caused civilizational disruption on a hemispheric scale, eliminating populations, erasing accumulated knowledge, forcing survivors to reconstruct the basic elements of organized life from a position of radical scarcity, then the beginning of what we call civilization is not a beginning. It is a recovery. What we label the Neolithic Revolution, the emergence of agriculture, animal domestication, settled communities, and early complex society, did not emerge from nothing. It may have emerged from the ruins of something older that we have not yet fully found. This reframe has consequences that extend beyond archaeology. If the conventional timeline represents the recovery phase of human history rather than the initial phase, then questions that seemed answered become open again. Why did agriculture emerge, apparently independently, in multiple locations across the globe, within a relatively narrow window following the Younger Dryas? The conventional answer is environmental. As the climate stabilized in the post-Dryas warming, agriculture became viable. But an alternative answer is also available. Human communities reconstructing the knowledge of food production that had existed before the catastrophe, rediscovering rather than discovering for the first time the practice of deliberate cultivation. Why do so many early civilizations appear, at their foundation, with levels of astronomical knowledge, architectural sophistication, and symbolic complexity that seem advanced for communities that, according to the conventional model, had only recently transitioned from hunter-gatherer life? The conventional answer involves rapid cultural development under conditions of agricultural surplus. The alternative answer is that these communities were drawing on inherited knowledge fragments of a deeper tradition, transmitted through the survival period, and reassembled as conditions allowed. Neither answer is provable with current evidence. The conventional answer has the advantage of not requiring anything to have been lost and recovered. The alternative answer has the advantage of explaining certain features of early civilizational emergence that the conventional model handles awkwardly. What the Younger Dryas impact hypothesis does, regardless of which answer one prefers, is force the question to be asked seriously. It places a major disruption event in the gap between the prehistoric and the historical, and asks what existed on the prehistoric side of that gap that we have not yet fully accounted for. The Gobi Glass sits in that gap. The silence in the sediment sits in that gap. The myths of burning heaven sit in that gap. Something happened in the space between what we know came before and what we know came after. That space is where the most important questions in human prehistory currently live, and the glass in the desert is one of the clearest physical markers of where the edge of that space lies. In the hills of southeastern Turkey, on a ridge overlooking what was once a productive, well-watered landscape, there is a structure that forces every serious historian of human civilization to pause and reconsider what they thought they knew. Göbekli Tepe, which translates, prosaically, as Potbelly Hill, was excavated beginning in 1994 under the direction of German archaeologist Klaus Schmidt. What he found beneath the surface was not what the conventional timeline predicted. Massive T-shaped limestone pillars, some of them weighing up to 20 tons, arranged in concentric circles and decorated with detailed, carefully executed carvings of animals, foxes, boars, vultures, scorpions, and serpents, rendered with an artistic skill that belies any assumption of primitive capability. The site dates to approximately 12,000 years ago, placing its construction squarely within the period immediately following the Younger Dryas onset. The construction of Göbekli Tepe required the quarrying and transport of multi-ton stone blocks over distances of hundreds of meters. It required the maintenance of a sufficiently large and organized labor force to carry out this work. It required the design and execution of a complex architectural plan extending over multiple construction phases. And it required, above all, a motivating purpose powerful enough to sustain this effort. A shared cultural or religious project of sufficient importance that communities whose survival was not yet secure invested enormous resources in building something that served no obvious subsistence function. Researchers have found no evidence of permanent habitation at Göbekli Tepe. No hearths for daily cooking, no evidence of storage or food processing. The site appears to have been a ritual center, a place communities traveled to and gathered at, not a place where anyone lived. This means that the communities who built it were organized enough to sustain specialized labor outside of immediate subsistence work, which implies a level of social complexity that the conventional model of the period did not predict. And then, crucially, hauntingly, the site was deliberately buried. Around 10,000 years ago, the builders of Göbekli Tepe filled in their own construction with rubble and sediment, covering the pillars, sealing the complex beneath the hill. This deliberate burial is what preserved it so completely to the present. It is also what is most difficult to explain. Communities do not typically bury their most significant ceremonial structures unless they have a powerful reason to do so, unless they fear what will happen to the structures if they are left exposed, or unless they are undertaking a ritual act of sealing and preservation. Some researchers have proposed that Göbekli Tepe was buried in response to climatic and social disruption following the Younger Dryas, that its builders, facing conditions that threatened their community's continued existence, chose to preserve their most important site against the possibility that the world as they knew it would not endure. This is speculation, but it is speculation that fits the circumstances with uncomfortable precision. The connection to the Gobi anomaly is geographic and thematic rather than direct. Göbekli Tepe lies at the western edge of the ancient productive corridor that extended eastward through Central Asia, the same corridor that the post-Dryas population movements traced, the same corridor where the glass fields lie. If a community sophisticated enough to build Göbekli Tepe existed at the western edge of this corridor during this period, the question of what existed at its center becomes more rather than less pressing. Göbekli Tepe is the cultural memory of the catastrophe, preserved in stone. The Gobi Glass is the physical memory, preserved in fused sand. They are separated by thousands of kilometers and connected by the same moment in time, the same planetary event that ended one world and forced the survivors of it to begin the long work of building another. What was in the Gobi that corresponds to Göbekli Tepe? What was buried there not deliberately, but by the catastrophe itself that we have not yet found? The question has no answer yet, but it is, increasingly, a question that serious researchers are willing to ask. History, at its best, is the practice of epistemic humility, the recognition that what we know is always a fraction of what happened, and that the fraction we know is shaped by what survived, what was found, and what the interpretive frameworks of our time were prepared to see. The Younger Dryas impact hypothesis and the accumulating evidence around the Gobi Glass anomaly invites a specific form of that humility. It asks us to consider that the human story has a hidden chapter, a period of complexity and catastrophe that precedes what we call civilization, that shaped everything that came after it, and that has been invisible not because nothing happened, but because the evidence for it lies in places and forms that conventional archaeology was not, until recently, looking for. Accepting this hidden chapter changes specific things. It changes how we read the mythological traditions of ancient cultures, not as pure imagination or as theological invention, but as possible repositories of real historical memory, encoded in the only language available and transmitted across time through the only mechanism available. It changes how we interpret the rapid emergence of agricultural complexity in the post-Dryas period from an unexplained acceleration to a possible recovery and reconstruction. It changes the questions we ask about unexplained astronomical knowledge and architectural sophistication in early historical cultures from anomalies to be explained away to evidence to be followed. And it changes something less tangible but perhaps more important: the story we tell ourselves about what we are. The conventional narrative of human history is one of emergence from simplicity, a species gradually accumulating the knowledge and social complexity that defines civilization, building upward from primitive origins toward the world we now inhabit. That story is partly true, but if the hidden chapter is real, it is incomplete. The fuller story is one of a species that reached toward complexity, was struck down by forces beyond its control, lost most of what it had built, and began again. That is not a story of steady progress. It is a story of resilience, of the specifically human capacity to survive catastrophic loss and reconstruct meaning from what remains. The myths, the languages, the glass itself, these are not just evidence of what was destroyed. They are evidence that something survived. The destruction carried what it could and kept going. That is not a lesser story than the conventional one. In some ways, it is more extraordinary because it describes a species that, even when the sky falls, finds a way to remember and to rebuild. The glass in the Gobi has been lying in the sand for 12,000 years, waiting for the right question. We are only now beginning to ask it. The investigation of the Gobi Glass anomaly is not a closed file. It does not belong to the category of historical mysteries that have been examined, debated, and then set aside for lack of new evidence to move them forward. It is, at this moment, an active area of research, one in which new analytical methods, new survey technologies, and a shifting intellectual climate within the relevant scientific disciplines are all converging to create conditions for the kind of progress that has not been possible before. The last decade has seen significant advances in the precision of isotopic analysis, the technique at the heart of glass field investigation, which reads the chemical fingerprints embedded in glass to determine what kind of event created it. New mass spectrometry instruments can resolve isotopic ratios to precision levels that were not achievable 15 years ago, and those finer measurements are beginning to discriminate between scenarios that previously looked identical at coarser resolution. Samples that were analyzed in the 1990s and early 2000s and returned ambiguous results are being reanalyzed with these new instruments, and in some cases the reanalysis is producing significantly clearer pictures of origin. Remote sensing technology has advanced in parallel. The latest generation of satellite sensors can detect surface mineral composition from orbit with sufficient precision to identify glass deposits that have not yet been confirmed through ground survey. Programs currently mapping mineral distributions across Central Asia for resources and geological characterization are, as a byproduct, generating the first comprehensive surface mineralogy maps of the Gobi region. When these maps are analyzed specifically for the silica-rich signatures of fused glass, The results will expand the known extent of the Gobi Glass fields considerably or confirm their limits. Either outcome is scientifically valuable. Access conditions have also been changing. Increased international scientific collaboration, driven partly by planetary defense research priorities and partly by broader geopolitical shifts in Central Asian scientific exchange, has made it easier for multinational research teams to conduct joint expeditions in the Gobi region than at any previous point in the modern era of investigation. Expeditions planned or recently completed by joint Chinese-European and Chinese-American teams have been designed specifically to collect samples from glass zones that have been identified but never chemically analyzed, and to conduct systematic subsurface testing in areas where glass deposits overlap with prehistoric tool scatters. The YDIH research community has matured in ways that benefit Gobi-specific investigation. The global network of researchers now documenting and analyzing YDIH marker layers at sites across multiple continents has established both a methodological framework and a comparative dataset that allows Gobi findings to be interpreted in their full planetary context rather than as isolated regional anomalies. A Gobi glass sample whose chemical profile is now compared against a database that includes YDIH marker layers from South Africa, Syria, and Chile is being read in a much richer interpretive context than a sample analyzed in isolation 20 years ago. The momentum is real. The tools are better. The framework is more developed. The community is more connected. The investigation of the Gobi Glass is entering a phase in which the rate of new discovery is likely to accelerate, and in which the findings are more likely to resolve toward a clear picture than to remain at the level of suggestive ambiguity that has characterized the field for decades. The desert is being read more carefully than it has ever been read before. There is a thread that runs through everything this investigation has uncovered, through the chemistry of the glass and the silence in the sediment, and the myths of burning heaven, and the genetic bottlenecks and the buried ritual centers. And that thread is not made of evidence. It is made of meaning. The evidence tells us what happened. The meaning asks us what to do with that knowledge. What the Gobi Glass teaches, if we are willing to receive the lesson, is something about the relationship between memory and survival. The communities that lived through the Younger Dryas catastrophe, whatever its precise form and mechanism, did not have writing. They did not have institutions designed to preserve and transmit knowledge across generations in the way that universities and libraries do. They had only the most ancient human technology. The story told by one person to another, in darkness, around fire, as a form of both connection and obligation. And they used it. The memory of what happened to them, the fire in the sky, the transformed landscape, the silence that replaced the world they had known was encoded into the stories they told and told and told again, across hundreds of generations, across thousands of years, across the diversification of languages and cultures that scattered their descendants across the Eurasian continent and eventually the world. The story changed form. It became mythology, then cosmology, then religious narrative. But it did not disappear. This is a form of civilizational resilience that deserves more recognition than it receives. The survivors of the Younger Dryas catastrophe were, in the most literal sense, living through the end of their world. The landscape they had known was being destroyed. The communities around them were fragmenting or dying. The immediate demands of survival in a suddenly hostile environment left little room for anything beyond the most basic acts of continuation. And yet they kept the memory. They passed it on. They found a way to encode the most important information: the sky can fall, the world can change in an instant, the green lands can become glass and sand in a form durable enough to survive their own deaths, and the deaths of everyone they knew, arriving eventually in the written records of civilizations that had no idea they were preserving the testimony of eyewitnesses. The linguistic diversity that emerged from Central Asia after the Younger Dryas is, in this reading, not just a historical fact about language development. It is evidence of the extraordinary cognitive and cultural vitality of the survivors, their capacity, even in the aftermath of catastrophe, to develop, differentiate, and ultimately flourish into the cultural multiplicity of the world we inhabit. The catastrophe did not end the human story. It fractured it, and, in the fracturing, scattered it across the world. Every language spoken today that traces its ancestry to the Central Asian post-Dryas dispersal carries, somewhere in its deepest grammatical bones, the genetic memory of communities that survived the Younger Dryas and kept walking. The stories in those languages that describe fire from the sky are not metaphors for human emotional experience. They are, in the careful reading of researchers who take the transmission of catastrophic memory seriously, the oldest eyewitness accounts in the world. The glass is one archive, the language is another, the DNA is a third. They are all saying the same thing, in different media, across different timescales. Something happened here, something enormous and fast, and the people who survived it did not let it be forgotten. 12,000 years of remembering. That is not a small thing. It is, depending on your frame of reference, either the most human thing imaginable, the refusal to let catastrophe be the final word, or the most humbling. The recognition that we are the inheritors of a story far longer and far darker than we knew, told to us in glass and myth and bone, by ancestors who had every reason to fall silent and chose instead to speak. There is a particular quality to the horizon of knowledge, not the comfortable boundary where the known gives way to the merely unknown, but the deeper edge where the unknown shades into the unasked. Most investigations stay well short of that edge. They work within established frameworks, answering questions that the existing vocabulary of a discipline can formulate and the existing methods can approach. This is how knowledge advances most efficiently, and there is nothing wrong with it. But every generation or so, in every field of inquiry, someone looks past the comfortable boundary and formulates a question that the existing framework cannot contain. The evidence accumulated around the Gobi Glass, the chemistry, the distribution, the silenced populations, the global parallels, the mythological convergences, the shifted timeline has brought us to exactly that kind of edge. The question that the evidence raises is not simply what created the glass, or whether the Younger Dryas impact hypothesis is correct, or how sophisticated the populations of prehistoric Central Asia actually were. Those are important questions, and they are being asked with increasing rigor by serious researchers. But beneath them, there is a larger question that the glass field in all its strangeness keeps posing, with patient and geological consistency, to anyone willing to sit with it. The question is this: how much of the human story is still waiting to be found? We build our understanding of ourselves on the evidence that has survived, that has been excavated, that fits within the interpretive frameworks we have developed. But the Gobi Glass is a reminder not the first, but one of the most vivid that the evidence is partial, the excavation is incomplete, and the frameworks are still being revised. There are layers in the sediment that no one has sampled. There are sites beneath the desert surface that no one has found. There are chemical signatures in rocks across multiple continents that have not yet been analyzed with sufficient precision. There is a chapter of human history that the conventional account does not contain, and the outlines of it are only now beginning to be legible. The glass has been in the desert for 12,000 years. It formed in an instant, in heat that consumed whatever existed in that place in that moment. It cooled. It was buried. The wind moved across it. The stars continued their slow rotation overhead, and it waited, with the absolute patience of inorganic matter, for the species that made it indirectly. Through the chain of causation that runs from cosmic event to atmospheric explosion to fused desert surface, to come back and ask what happened. We are here. We are asking. The answer is not yet complete, but it is closer than it has ever been. The desert is quiet in the way that places with long memories are always quiet. Not empty, full, and dense, and patient.